way to keep working towards drawing graphs with calculus now, we're going to look at the end behavior of the graph, which is something that we've done before, but I'm going to introduce, a new thing to show you the kind of calculus approach to it. So we're going to start with the basics. If we're graphing end behavior of a polynomial function, okay, and here's just a general formula for like a polynomial. We've got ax to some power, and then the next term, the power on x is 1 less. It'll be 1 less, 1 less until you get down to where it's 2, then 1, then none. So if you remember the rules for this, we're only concerned with this leading term, because end behavior is really what's happening as we're going towards infinity and towards negative infinity. Those are the two ends. So if I'm looking at what's happening as x gets very close to infinity, or as x gets to be a very large number, this leading term here is going to far outweigh anything that the rest of these do. Because let's say I put in 1,000,000. If I have 1,000,000 to the 8th power, that 1,000,000 to the 8th power is going to overshadow the 1,000,000 to the 7th power. Okay? Because it's times another 1,000,000. Okay? And infinity is way bigger than 1,000,000. So, times another degree of infinity just completely overshadows the rest of the polynomial. So our end behavior is only determined by this leading term. So let's say n, so our highest degree is an even number. That's going to tell us, are the two ends doing the same thing or opposite things? So that's what n's going to determine. If I put a large positive number in here, and it's to an even power, it's going to come out to be positive. If I put a large negative number in for x and take it to an even power, it's also going to come out to be a positive number. So if n is even, then our n's are doing, we have the same end behavior. Okay, and if they're odd, so if I have like to the 3rd power here, if I put in a positive, I get out a positive. If I put in a negative, I get out a negative. So here we get opposite end behaviors. And what they actually do depends on what a is. So here, if I put in a large positive or negative number, I'm getting out a large positive number. So if a is also positive, I'm taking that large positive, multiplying it by a positive, and getting a positive out. So my end behavior, both ends are going to be going up. If a is negative, it's going to be taking that large positive number at both sides and flipping it so that both ends will be going down. Okay. Now in between here, we can have lots of curves and things like that. But the end behavior is this. If n is opposite, or if n is odd, then we're going to have opposite end behavior. So if I put in a large positive, I get out a large positive. If I multiply it by a positive, it stays positive. If I multiply a large negative by a positive, it stays negative. And if a is negative, it's going to reverse these two. So I get that end behavior. So here's some quick examples here. Here I've got an odd power with a negative coefficient. So my left end is going to go up, my right end will go down. Here I have an even power with a positive coefficient, so both ends are going up. Odd power, positive coefficient, the right side's going up, the left side's going down. Even power, negative coefficient, both sides are going down. Okay, if we look at rational functions, we used to have those rules where we looked at the leading coefficients to kind of determine that. And you can still use those, which is fine. I want to introduce L'Hopital's rule because this is kind of an easy case where we can see it working. And then when it comes up later as we're going through, we can revisit it and you will have already seen L'Hopital's rule. Basically, L'Hopital's rule, you're going to use it when you get one of these cases. So when you're taking the limit, because that's really what we're doing when we're looking at end behavior, we're taking the limit as x approaches infinity. We want to know what the function's doing as our x values get closer and closer and closer to infinity, and as they get closer and closer and closer to negative infinity. So this is like the right side, and this is the left side of our function. So let's say we take that limit and we get one of these four indeterminate forms. They're indeterminate because they don't really have an answer. 0 divided by 0, we don't know what that is. We know you can't divide by 0, but we also know that if you divide something by itself, it should be 1. So this is kind of on the border of two different rules, so we're not really sure. It's indeterminate. Okay, and infinity over infinity, well, we don't really know what that is either, because, you know, infinity means it's increasing without bound. It's just constantly going up. So if these are both constantly gaining in power, we don't know which one's going to overtake the next. We don't know if this infinity is growing faster than that one, or maybe the bottom one's growing faster than the top one. We really don't know. The same thing if we throw a negative in there. We don't know what's happening. So if you have one of these indeterminate forms, you can use L'Hopital's rule, which basically means if we get one of these, instead of looking at the original limit, we're going to take the derivative of the top and the bottom separately, and then take the limit of the derivatives to see what the actual end behavior is, or what the limit is. So let's look at some that we already know the answer to. Okay, if we use our old rules with this first function, okay, I have a higher power on the top than I do on the bottom. This is actually one of our special cases, which I'll get to later. But so using our old rules, I would know that as I approach positive infinity, okay, so the limit of this as x goes towards infinity, okay, the top's going to be growing faster than the bottom. So I'm going to have a much larger number on top than I do on the bottom, and this is going to equal infinity. Okay, the left side behavior, or the limit as x approaches negative infinity, okay, I'm going to have, if I put a negative infinity here, it's going to be to the fourth power, which is going to come out positive. So I'm going to have a positive infinity over a much smaller negative infinity, but it is going to be positive over negative, and this is going to approach negative infinity. Okay, now let's look at how we actually take the limits of these. So if I actually take the limit of this whole thing, when I put infinity in, I'm going to get infinity over infinity, which would be an indeterminate form. So then I'm going to want to take the derivative, okay? And really, I don't need to worry about these derivatives, because I know eventually as I continue taking the derivative, these are going to go away, but we'll just go through it. So the first derivative is going to be 20x cubed plus 9x squared minus 7 over 6x squared minus 10x plus 1. If I put in infinity again, I'd get infinity over infinity, so I can use L'Hopital's rule again, and I'm going to get 60x squared plus 18x. At the bottom, I'm going to get 12x minus 10. I'm still going to get infinity over infinity, so I'm going to take the limit one more time. I get 120x plus 18 over 12. And now if I put in infinity, I'm going to get infinity over 12, which is infinity. Okay, so it's perfectly fine if you guys use your old rules. They're a little bit quicker in these cases, but I do want you to just know what L'Hopital's rule is. If I do negative infinity, I would kind of go through the same process. I'd be getting, you know, infinity over negative infinity, then I'd get negative infinity over positive infinity, so I can keep using L'Hopital's rule. I'd get positive infinity over negative infinity over 12, which would be negative infinity. And then I'd get my end behavior that way. Okay, so here our old rule would tell us we have the same power, so actually we're going to approach the fraction we get with our leading coefficients. Okay, so we're going to have a horizontal asymptote at 5/2. Okay, so at 5 halves, I would have this horizontal asymptote, and I'd be approaching that as we shoot towards infinity. So using L'Hopital's rule, we're going to see the same thing. L'Hopital's rule, if I put infinity in, I'd have infinity over infinity, take the derivative, and I'd get 20x cubed plus 9x minus 7. Okay, I'd get the same thing that I had up top because it's the same thing except my power on the bottom would stay one higher. So as I keep going through this, I'd get 8x cubed minus 10x plus 1. Take the derivative again. 60x squared plus 9 over 24x squared minus 10. One more time, I'd get 120x over 48. And then take the derivative one more time, and I'd get 120 over 48, which reduces down to 5 halves. Okay, so that's what my limit as I approach infinity is. And that's going to be the same as I put a negative infinity in here. Okay, because negative infinity, I'm going to have infinity over infinity, then I have negative infinity over negative infinity, then I have infinity over infinity again, then negative infinity over negative infinity, and then I would just have 120 over 48, which is 5 halves again. Okay, so I think you guys kind of get the point. This one, I'm going to end up with, as I take my derivatives, I'm going to end up with a number over infinity, which we know is 0. Okay, so if I have a number over infinity, and I'm taking I'm taking a small number divided by a huge, tremendous number. So I've got this teeny tiny fraction, which is basically 0. The special case that we have is when your top power is exactly 1 degree higher than your bottom power. And I just want to remind you that we're going to have a slant asymptote in this case. So our end behavior will still be the same. We're still going to be approaching infinity and to the right and negative infinity to the left. But I do want to go through this just so that when we start actually graphing our whole functions, you can apply your slant asymptotes. So what we're going to do, we're going to do long division, which everybody loves. Okay, I'm going to divide the top by the bottom. Okay, and then remember, I need the first term of this to match the first term of this. So I'm going to need an x. In order to make a 2 turn into 3, I'm basically going to cancel the 2. Okay, so I'm going to divide by 2 or times by a half, and then I'm going to multiply by the 3 so that I end up canceling the 2 and replacing it with a 3. So if I multiply 3 halves x by each term here, I'm going to have 3x cubed. This would be 15 halves x squared. And this would be minus 3 halves x. Now notice, I don't have any x's up here, so make sure you don't combine the 5 with the 3 halves, because they're not like terms. So I've got this, and now I have to remember that I'm dividing or subtracting. I'm subtracting all these, so all my signs are going to change. Okay, and I end up getting these cancel. These, when I add them together, I'm adding 8 halves and 15 halves for a total of 23 halves. Negative 23 halves. These, I don't have anything to add to the x term, so it just comes straight down. And I'll take the minus 5 down also. So now I need this to match this. So I'm going to have to multiply by, let's see, we have to multiply by 23 fourths. So negative 23 fourths x. Oh, I don't even need the x. I just need the 23 fourths. Okay, because when I multiply this by that, I end up with negative 23 halves x squared. When I multiply here, I'm going to get negative 115 fourths x, and then I'm going to have positive 23 fourths. Okay, change all my signs, add these up. These will cancel. This is really 6 fourths, so that leaves me with 121 fourths x. Combine this. This is the same as 20 fourths. So negative 20 fourths minus 23 fourths is negative 43 fourths. Okay, and this is my slant asymptote. Okay, this is the equation of my slant asymptote. So I don't want to graph that. Okay, this is my y-intercept, my slope. I'm going up 121 and over 4. Okay, so I just made this one up so you get kind of a crazy thing to graph, but this would be your slant asymptote. One other thing we need to go over for end behavior is if we have a case where we can't use our old rules, and L'Hopital's rule would fail here, because L'Hopital's rule, you can try it for yourself, but if you take the derivative of the top and then the derivative of the bottom, it's still going to be an indeterminate form. If you do it again, you're going to end up right back where you started, basically. So it just keeps flip-flopping. So the other option is we're going to want to change this. We're going to change the top and bottom by multiplying by the highest power of x over itself. So on the top, I'm going to multiply by x over x. So I'm just basically multiplying the top by 1, which is legal. And on the bottom, inside the square root, okay, I'm going to multiply by x squared over x squared. So on the top, this is going to transform it. I'm going to have, actually, sorry, I misspoke. We're going to want to multiply the top and bottom by 1 over x. Okay. Now, in order to multiply the bottom by 1 over x, in order to get it inside the square root, I'm actually going to have to square it. So I'm kind of multiplying by the square root of 1 over x squared. So let's look at the top first. If I have 3x minus 2 and I'm multiplying that by 1 over x, that's going to leave me with 3 minus 2 over x. On the bottom, I'm taking this square root and I'm multiplying it by this square root, so I can combine in the same square root there, which will give me 2x squared over x squared plus 1 over x squared, all in the square root. And then these will cancel. So I'll copy the top down. On the bottom, I've still got this square root, but now it's just 2 plus 1 over x squared. And now as I take my limits, as x goes to infinity, I can actually plug that in. And on the top, I'd have 3 minus 0, because the limit of this is 0. And on the bottom, I'd have the square root of 2 over, or the square root of 2 plus 0. So there's my limit as I approach the right end behavior. And if I do negative infinity, okay, now as I put negative infinity into this, I'd have 3 plus 2 over a big number, which is still going to be 3 plus 0. Or actually, as I do negative infinity, I'm going to have to change a little piece of this. Because now as we're looking at large negative numbers, x, okay, if I do this, I'm going to end up with a positive. Okay, it's always going to make it positive, so I need to make a little change here. I need to actually make this negative square root of 1 over x squared, because I don't want to put my negative infinity in and have it come out to be a positive all the time. I want to keep that negative part. So that's just basically going to change this to a negative here. Or not a negative there. It'd be, this would be, yeah, it would have a negative out front here. Okay, now as I put in my negative infinity, I'm going to get 3 over negative square root of 2. So I've got 2 horizontal asymptotes. As I approach the right, so as I'm going to the right, okay, my function is going to approach, this horizontal asymptote. And as I approach negative infinity, it's going to approach this other asymptote down here. Okay, and you can see this example again. It's on page 202 in your book if you want to look at it, the way they do it.